Good morning. I am Dr. Vemula Himamaheswara Rao, Assistant Professor of Physics, Department of Freshman Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Welcome to the lecture series Atomic and Molecular Spectroscopy. Today we are going to discuss spectroscopic terms, how to calculate spectroscopic terms for multiple electron atom, particularly electrons, more number of electrons in outer configuration, outer electronic configuration. So let us see. We already uh, discussed how to calculate spectral terms for single electron atoms such as hydrogen. Not only hydrogen, for even for atoms of having outermost orbital electron configuration is 1. That means that means valence electron is 1. So here this is the method of uh, calculating J values, multiplicity values, and L value, spectral term L values. So these are all the spectral terms for one electron atom corresponding to n equal to 3. So let us once again consider hydrogen-like atom. So here for hydrogen-like atom, for example, 1s electronic configuration is 1s. So here s spin angular momentum quantum number s will be equal to 1 by 2, and orbital angular momentum quantum number L equal to 0, as it is S orbital or S shell. So now total spin angular momentum will be equal to 1 by 2, S equal to 1 by 2. So then multiplicity will be equal to 2s plus 1. 2s plus 1 means as S equal to 1 by 2, 2 into 1 by 2 plus 1, that is equal to 2. 2 is the multiplicity. And now L, total orbital angular quantum component L equal to, so here only there is only single electron L, that value is 0. So the spectral term should be denoted as S. L value 0, that means the spectral term is S. And J value, total angular momentum quantum number J, we can calculate this value by taking L minus S, L minus S to L plus S in steps of integral number L plus S. So here L is 0 and S is 1 by 2. So 1 by 2 minus 0 to 1 plus 1 by 2 plus 0. So that means 1 by 2, 1 by 2. So can get only one value for total orbital angular momentum quantum number. So the finally the spectral term can be written as first spectral term S, and the multiplicity on the left superscript of S is 2. This is the multiplicity. So we can write multiplicity here. and J term is written here. So this is the spectral term for hydrogen atom. So this is the energy level or energy state for the hydrogen atom, and it is also the term energy level for ground state. This is the ground state spectral term. So this is not only the ground state spectral term for not only for hydrogen atom, but it is also for ground state energy term or spectral term for any atom like hydrogen having single uh, electron in s orbital, like 2s, 3s, 4s, like that. So only if there is only one electron, even in 2s, 3s, 4s, we can see 2s 1 by 2 is the ground state energy level for all those atoms. So here we can see this is the one state, that is only the ground state, ground energy level, or spectrum for ground energy level for electrons, single electrons in the orbitals like 2s, 3s, 4s. These numbers indicates the principal quantum number or orbital number, second orbital, third orbital, fourth orbital. And again, if we see single electron, so that is the calculation part, how to calculate the spectral term for single electron atom in s orbital. If there are single electron in p orbital, we can calculate, we can follow the same procedure. So there also, for example, 2p, if we take 2p electron, then s value, s as it is single electron, s is 1 by 2, l equal to 1, then multiplicity total spin angular momentum will be equal to s equal to 1 by 2. Then as said to the earlier uh, atom, multiplicity m equal to 2s plus 1 will get 2 only, and again total orbital angular momentum l equal to same l equal to 1. So the spectral term will be uh, for l equal to 1, we'll see p is the spectral term. Okay, so j value will be from l plus l minus s to l plus s, so that l value is 1, s value is 1 by 2. So 1 minus 1 by 2 to 1 plus 1 by 2, that means 1 by 2 comma 3 by 2. These are the j values. So that the spectral terms, finally this is the multiplicity, this is the term, spectral term, and these are the j values. Final spectral terms can be written as 2p 1 by 2 and 2p 3 by 2. These two are the spectral terms for the 2p electron. That means if there is an electron in the p orbital, either it is in the second orbit, third orbit, or fourth orbit of that, so we will get same spectral terms. Okay, same spectral terms. When the electron is in the p orbital, like 3d, 4d electron, or 5d electron, then we will get 2D 3 by 2, 2D 5 by 2. Similarly, we can get for F orbital also. For F orbital, like this 4F, 5F orbitals, we will see the spectral terms as 2F, 5 by 2, 2F, 7 by 2. So we can show these terms by calculating following the same procedure. Okay, all this procedure is for single electron atoms, and that electron, even for example, let us see the periodic table here. The 1s electron, that means here we discussed about the hydrogen like atom. So hydrogen like atoms here, lithium, sodium, potassium, rubidium, cesium, francium, all these are hydrogen like atoms. That means the outermost electronic configuration contains single electron, SR, electron in the S orbital. So here this is 1s electron, this is the 2s electron, 3s, 4s, 5s, 6s. So all the atoms having the energy terms or spectral terms only 1s, 2s, 1 by 2. Okay, so there is no splitting of this spectral term for single electron, and these terms, maybe these atoms, all these atoms are under alkali atoms, alkali metals. All these elements are alkali metals. And these are also called. There are two electrons here. The configuration is 2s2. There are two electrons in the s orbital. So these are called alkali earth metals. Okay, next let us see multiple electron atoms. When there are two or more than two electrons in the outermost orbit of that. So let us. There are also two cases. One is when the two electrons are in the non-equivalent optical electrons or equivalent optical electrons. So let us consider first non-equivalent optical electrons such as 4p, 4d. So there are two electrons in the two different orbitals. Then those are called non-equivalent optical electrons. Optical means they are in the outer side of the orbits, outer orbit, outermost orbit electrons. The remaining electronic configuration is completely closed. Okay, so here there are two electrons, 4p, one is in the p orbital and one is in the d orbital. So this must be an excited state of germanium. In general, germanium electronic configuration for germanium, Z equal to atomic number Z equal to 32. So the electronic configuration must be like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2, 4, 6, 10, 12, 18, 20, 30, 32. So there are 32 electrons in different orbitals. So the outermost orbital electron configuration is 4p2 here for the ground state of the germanium atom. But whenever one electron is jumped to the next subshell, then it will come 4 as 4p 4t. That means this is the one of the excited state of germanium atom. So now let us see how to calculate spectral term to indicate spectral term for this energy state or energy level. So here there are two electrons. The spin values for first electron is 1 by 2 and for the second electron is also 1 by 2. Same for the both the electrons, and let it be S1. For the second electron it should be S2. Here we must remember that the electron uh, spin correlation comes first whenever we consider LS coupling. Generally for the lower atomic number atoms, or the atoms, lighter atoms, for the lighter atoms we must go through the LS coupling. So the interaction must be LS coupling. So whenever LS coupling is in action, the interaction between spin correlation comes first. The spin interaction is stronger. So that the combination of these two electrons, for the combination of these two electrons, we must find out the total spin angular momentum component. So for that, total spin angular momentum S must be equal to, here also, S1 plus S2 or S1 minus S2 to S1 plus S2. As these two values are same, we must get 1 by 2 minus 1 by 2 to 1 by 2 plus 1 by 2. So this is the procedure to find out the total spin angular momentum quantum number. So the spin angular momentum should be either 0 or 1. So then the multiplicity values m should be equal to 2s plus 1. That means one value for s equal to 0, m value 2 into 0 plus 1, that means 1. For s equal to 1, the multiplicity m must be equal to 2 into 1 plus 1, that means 3. So there could be singlet and triplet terms. Singlet and triplet. So these are about the S values. Now let us come to L values. So there are two electrons. So L1 equal to L1 is equal to, for P electron, L1 equal to 1, and for D electron, that means L2 equal to 2. Now again, total angular momentum L must be taken like L1 minus L2 to L1 plus L2 in terms of integral steps. Okay, so here let it be 1 minus 2 or 2 minus 1, anyway 2 minus 1 to 2 plus 1. So 1 will get values 1, 2, 3. So these are the L values. So the L values are 1, 2, 3. So these values corresponding to the L equal to 1 means P, 2 means D, 3 means F spectral terms. So there are three spectral terms P, D, F. Okay, so here this interaction, electrostatic residual interaction, is also stronger after spin correlation. So after spin correlation, we must add up electrostatic residual interaction, which is due to the Coulomb force. Okay, then LS coupling, that means spin orbital correlation occurs. That means spin orbital interaction occurs. So total spin angular momentum quantum numbers S values are 0 and 1, and total orbital angular momentum quantum numbers L values are 1, 2, 3. So in order to calculate J values, we must follow like this. So for S equal to 0 and when L equal to 1, then J values. J values, total orbital angular momentum quantum numbers must be L plus L minus S2, L minus L plus S, so that we'll get 1 minus 0 to 1 plus 0. So only 1. Okay. Whenever S equal to 0 and L equal to 1, 2, L equal to 2, the J values are L plus S2, L minus S2, L plus S. So here also we will get 2. When S equal to 0 and L equal to 3, J values are only one value 3. Okay. So we are getting J values 1, 2, 3. And again, whenever S equal to 1 and L 1, then J values 1 plus 1 to 1 minus 1. So that means 2, no, follow the increasing order. 1 minus 1 to 1 plus 1, that means 0, 1, 2. Okay. And again, when L equal to 2, J values are 2 plus 1 to 2 minus 1, or 2 minus 1 to 2 plus 1. That means 1, 2, 3. And when S equal to 1, L equal to 3, J equal to 3 minus 1. That means 2, 2, 3 plus 1, 4. So 2, 3, 4. We are getting 2, 3, 4. Okay. So if we write the spectral terms corresponding to these combinations, you can write like here. S is 0. For all these terms, the multiplicity must be equal to 2 into 0 plus 1 means 1. The multiplicity is 1. So here for this particular spectral term, spectral energy level, so the spectral term is S. Multiplicity is 1 and L value is 1. That means P, 1P, J value is 1. And here multiplicity is 1, L equal to 2, 2 means D, and J value is 2. And for this, multiplicity is 1, L equal to 3 means uh, F, F, and J value is 3. So these are the singlet terms for the 4p, 4d electrons. These are the singlet terms. There are three singlet terms, 1p1, 1p2, 1f3. And these are the triplet. Why? Because s equal to 1, multiplicity is 2 into 1 plus 1 means 3. So these are all triplet terms. So that here the spectral terms 3, L equal to 1 means P, P, 3P. So J values 0, 1, 2 means 0, 3P, 1, 3P, 2. So these are the triplet terms. And here for this 3, L is 2 means D, 2D, here it is capital. 2D, J values are 1, 3D, 2, 3D, 3. And here multiplicity is 3, L is 3 means F, and J values are 2, 3, 4 means 3F2, 3F3, 3F4. So there are uh, three terms for each L value, each value. Okay, and these terms again splits based on the J value. So if J based on J value, it splits into 2J plus 1 spectral lines for the phase structure of the spectral lines. So based on the energy values, we can indicate all the spectral lines like this. In general, 4p4d term based on the spin-spin correlation, the energy levels are for S equal to 0 and S equal to 1 can split like this. So the higher multiplicity term having lower energy value. So based on this, S equal to 1, S equal to 1 is having lower energy value. And again, the L value, if the L value is more, energy is less, having lower energy. So in this case, for singlet, if you observe, these are the singlet terms. These three are singlet terms. So they have higher energy than triplet terms, all these terms, so that we can indicate like this 1P, 1D, 1F, including the J values. Here also, these are all having higher energies, and again based on L value. If L is higher, energy is less, so they are indicated with lower energy. So here L equal to 3, L equal to 2, L equal to 1. Higher L value having lower energy. And again here, these are the triplets, so lower energy. Then singlets, lower energy. If S is higher, energy is less. Among them again, the terms, see, based on L value. Higher L value having lower energy, and these also based on J value. Each 3F terms based on J value. If J value is less, J value is less, energy is less. Energy is less. So J value less, energy is less. As the J value increases, energy values increases. So like that, all the terms are indicated in this diagram. And again here, each of these terms split into individual spectral lines based on the J value into 2J plus 1 values. So if you calculate 2J plus 1 for all the spectral lines, you will get around 60 spectral lines. 60 5 spine 5 structure of spectral lines. Okay, so those splitting will be discussed in the later lectures. So here we can see spectral terms for 2 electron atoms SS, SP, SD, PP, DD for practice. Okay, so thank you all.
Like, share and subscribe. Hit the bell icon for more updates.